Hello everyone. Can you guys hear me? Let us begin with our session. I'm Sarah Masood. I work at Red Hat in the data science team. The past 1 year I've been working in this field, and today I'll be taking an introductory session on introduction to pandas. And in this talk, we'll listen about what is pandas, why we need pandas, how we create data frames in pandas, go about performing basic operations in there, and what else can we achieve using pandas. So let us begin. For those of you who joined now, the link to the repository where all the code is available is has been shared in the chat, both in the PyLadies remote chat group as well as in the uh, Google Hangouts chat. You can go visit that page, and if you want to go about working as we discussed, then you can download this repository and open all these notebooks, and you will have the relevant code there. And also, there are commands to obtain the data set that we will be using during the session. The Diamonds data set is a little huge and it might take some time to download. So depending on your network availability, you may want to download it now or you can do it later as well. So let us start. So first of all, why do we need pandas? Now, if you have used Excel or SQL before, then pandas will seem somewhat similar to Excel. But the problem with Excel, the good thing about Excel first is that it can help you quickly analyze the data and give you insights very easily, and you don't have to be a programmer to be able to use Excel or generate insights from that. But the problem with Excel is that it cannot handle huge amount of data. Sometimes some data set that I load into Excel actually crashes it while loading. Or it can happen that your data set is very partial in nature, it has incomplete values, it has a lot of junk in it. And if you go about cleaning the data set in Excel, then it involves a lot of manual process. And if you do this for similar data sets, then in Excel you have to do that manual process again and again until and unless you write macros to handle that. All of this is taken care by the Pandas library in Python, which was developed for the purpose of data analysis. So it can take care of huge data set. At the same time, it can take care of data set from multiple file formats. In addition to that, you can have time series analysis in pandas, and all of it can be then written into a script, and you can use that script to perform similar operations again and again. In fact, let us now see how to use it. So the first thing that you do is import pandas. Now here we have imported pandas, numpy, and matplotlib. These are the three things that you usually use together when you're dealing with some analysis in pandas. There are fundamentally two data types in pandas: the series data type and the data frame data type. And the only difference between the major difference between these two is that the series data frame is a one-dimensional data frame, whereas the data frame data structure is an n-dimensional data structure. So in series, you have a 1D array, but unlike any normal array or a normal list in Python, it has a corresponding index which you can specify. So when we create a Pandas series data structure S1, you see that we specified the range to be all odd numbers from 1 to 10, which we get. In addition, you see that the index values are explicitly mentioned and they start from 0 like any other indexing in Python. If you want, you can also create the series object from a dictionary. When you do so, then the key becomes the index and the value at that key becomes the value of your uh, series. Let us execute these and see what results we get, although the results are already shown in the output. So you see, when this operation is run, we get this result. Similarly, we can create our series using the dictionary values. And if you want, you can explicitly specify the index value. Here we have specified PQRS to be our index, and the name actually gives the name to the series. So the series S2 will actually have a name 1, and its index is being PQRS, corresponding to the first, second, third, and fourth value present in our series. Series data structure can be obtained using other data structures in Python and has a lot of operations that can be performed on it. But in our session today, we will be focusing on the other data structure, the data frames. Data frames are n-dimensional array. And in this n-dimensional array, you can have, or you will have indexing on both the rows as well as the column. Now, having such an indexing is very useful because it helps us identify the data very quickly. It can help perform automatic data alignment when you're combining two or more data frames together, and it helps in faster subsetting. Each of these features of the indexes you will see as we proceed throughout the course. You can create a data frame from an existing series, like we used the S2 series to create the data frame. Here, PQRS become our index values for each of the row, and the name of the series that we gave now becomes the name for the column. Now, data frames can be created from lists, from dictionaries. They can have explicitly defined index. You can create a data frame from another data frame or even a combination of series. But the real power of data frame comes into picture when we are importing data from different file formats. In fact, if we look at the official document, then these are the various file formats that are supported by the Python data frames. Here you see that CSV, JSON, HTML, Excel, almost even SQL, so all major file formats are supported, which means that in order to work with multiple file formats, you don't have to jump between software to software. You have one library to take care of that. And the syntax for reading and writing data into the various file format is very easy, which is that you specify the name of your data frame, and then you call pandas read underscore CSV, in this case because we are reading a CSV file, and then you specify the file name. In the generic format would be data frame name, pandas, read underscore the format that you're dealing with, which can be CSV, JSON, Excel, and then your file name. When you do so, then the data frame named df2 loads whatever data was present in our wine.csv file. To see what that data is, we can use the head function. By default, the head function will give you the first 4 or 5 values of your data set, and you can also specify how many values you want. So if I specify head 2, then I get 2 values. Now you see that here we have an strange column called unnamed 0, which has value 1 and 2. This is happening because in our wine.csv dataset, we have a column which is the index for each of the row present inside the CSV file. But Pandas does not know this. We can tell Pandas explicitly which column in our data set to be used as the index for the rows. In this case, we do so by specifying the index.call parameter. And when we do so, we see that the unnamed 0 column is gone, and now our index starts from 1, the value that was present at the first position of the unnamed 0 column. Similarly, writing to a data frame is equally easy. The syntax being, now this time we already have a data frame which we want to write. So you call that data frame and use the to function, to followed by the file format, which can be again CSV, JSON, Excel, and you give the file name under which it will be saved. In our case, I want the data to be saved from the in a JSON format. Now you see that we obtained the data in a CSV format, but we are saving it in a JSON format. And this is the real power of using the Pandas data frame, the the file format support that it provides. Let us see how we can use this further. This brings us to the end of the first chapter, where we discuss about what is Pandas, why we need Pandas over Excel, and how can we load basic data frames into Pandas. One point I would like to make is that in case of Pandas, it is not something to replace Excel. We use Pandas as a complement to Excel, where you analyze huge data, you clean the data, and after you have obtained considerable analysis from it, you can save that knowledge in an Excel sheet and share that Excel sheet with people who are not familiar with Pandas. Now, in this session, we will be talking about performing basic statistical operations on the data that we obtained. Again, first I'm creating a series data set which has the value 1, 2. NP_nan is a function that or a feature that returns you a nan value, which is not a number, and I'm specifying my series to be named as num. Once I've obtained my series, I create a data frame from that series, and this is what my data frame looks like. Now, because we did not specify any index in our series, data frame will explicitly take the default index of the series as 0, 1, 2, 3, and the name of our series becomes the name for the column, and we have our values here. Now we can one feature of data frames is that you can easily add new columns. Now it happens a lot of time when we are analyzing data, we want to add a new column or a new feature field which does not exist. Usually this feature field is a combination of one or more existing fields. For example, I have a data set that is 1 year old and I want to update, let's say, the age parameter within my data set. Then I can simply create a new column of now present age and use the df age, which is the existing age, and add 1 to it. Now the data set will explicitly apply 1 to each of the value present in the age column, and it will generate the new age for me. Similarly, in our existing data set, I create a new column called value, which is nothing but which multiplies by 2 each of the value present in the num column. What happens internally is that each value in our num column is multiplied by 2 and the result is saved in its corresponding row value column, and this is what we get. You see that for a nan value, the result is still nan. It does not do because Panda does not know what to do with it. Now, if you see the length of our data frame with respect to the num column, which then it is going to give us 4 because we have 4 values from 0 to 3. But an interesting thing happens when we perform the count operation, which returns us the value 3. The length operation takes into consideration all the rows, irrespective of what value they contain. But the count function takes into consideration only those rows in our data set that have numerical values or even non-numerical values but countable. None cannot be counted, and therefore when the count operation happens, the second row is ignored and we have the result as 3. Similarly, when I perform other statistical operations on the num column, let's say mean, then I see that the mean again ignored the nan value because the sum of column num will be 1 plus 2 plus 3, which is 3, divided by 3 values that are not nan, row 0, row 1, and row 3. So the mean comes out to be 6 by 3, which is 2. Similarly, for sum, you see that the sum again ignored the nan value. Similarly, for median, it will ignore the nan value, and all the statistical functions, in fact, will ignore the nan value. Until previous versions of Pandas, this was a problem, and you had to explicitly specify to all of these functions to ignore the nan value. Otherwise, they would return a nan result. But the latest versions of Pandas have taken this into consideration and have improved this function such that it in itself will ignore the nan values. You can also find the minimum and maximum value present within the data frame num column. You can obtain all of the description that we had seen so far using just one command called describe. Now, what describe function does is that on the describe function works on only a numerical data type. So the numerical column num, when we apply the describe function, it will give us the count, mean, median, mode, the minimum, maximum, the median, the 75 quartile, and the 25th quartile as well. And this is more clean way of obtaining obtaining a summary of our numerical data. We have another function which is the cumulative sum, which will cumulatively add the values. So for our num function, the first value is 0. The second value, if you remember, was 2, but the result will be 1 plus 2, which will be 3. And the third value was 3, but it will add 3 to it and return 6. You can also perform the statistical operation not only on just one column of the data frame, but on the whole data frame itself. Here again, the mean will be calculated for all the numerical columns or all the columns that are of numerical data type, and it will return the mean. So here we see that the mean is returned for the numerical column num and the second numerical column value. If I had a non-numerical column, let's say, which had a string of name, then that column would not be returned while determining the mean. Similarly, you can find the correlation between all numerical values. So on the on the left hand column, you see that we have num and values as row and num and values as column. So depending on how many number of numerical columns you have, you will have that many number of rows and columns. You see, and one thing that we should remember is that when we are finding the correlation, then the correlation of the value num with itself will always be 1. Interestingly, the correlation for num with value is also coming out to be 1 because we know that we multiplied the num into 2 to obtain the value column. But again, we should remember that if we are obtaining a high correlation value or even a correlation value of 1, then it doesn't mean that there has to be a relation that influences one value, that influences the value of one parameter by another. It requires further analysis to be able to determine that. Another simple method of obtaining the summary of the statistical value of a column in a data frame is the plot column. You can also give the whole data frame to be plotted at box. In this case, we have just one box for num. If I do it for all the numerical columns, then I will have as many boxes. Now, what this box represents is that the box itself is the interquartile range. That means that 50% of my value should lie within this box. The red line you see determines the median value within my data set. And the upper is the 75 quartile and the lower one is the 25th quartile. This is a very clean box that we have obtained, and this because the data set that we had was very clean. In real life, this might not be the scenario. Before moving forward, let us see if we have any questions up till now. Let's move forward. Let us now read an original data set or a real value data set and see what box plot we get out of it. So I'll load the diamond data set, and it will have a length of it has a length of approximately 600,000 values. And if we look at what these values are, then we get the first 5 values as all the properties associated with the diamond, whether it is the price, its measurements, the certification, the color, the carat value, etc. Right now, we're not interested in these in knowing what these values are, but we see that there are a lot of nan values associated with the price. While calculation, we do not want the price value to be none because it doesn't seem proper that price cannot have any value associated with it. One thing that we can do is that we can fill all the nan values with 0. That means all the places where price or any other column has a nan value, that will get replaced by 0. But one thing to remember is that this does not do an in-place filling. That means even though I see that the result here is 0 for the price values when I do a fill NA, but if I go back and see my head of the data set again, I see that it is still none. That is because I did not assign my data frame that is because I did not assign a new data frame after I performed the fill any operation. When I do so, then I will see that the nan values are gone. One of the functions of the data frame is the columns, which returns you the name of all the columns present within your data set. And in case you have categorical values, then you can determine what are the various unique values are present in your categorical value. Here, in case of color, we see that the categorical value is from E to H, which means that of all the 6,000, approximately 6,000 rows that we have, each of the row has either of these values present in it. When I perform the describe operation, I again obtain the mean, median, and all the quartile values for all the numerical data set, which is the price, the measurements, the carat value. But we also know that there are some non-categorical values as well. Let us try to plot one of the values, that is the x, which represents the length of our diamond data set. Because this is a huge data set, then the processing will take time. Now you see that the box plot looks a little different. Here we have here we see that some black lines have been introduced. Again, the box itself represents the interquartile range, with median at the red line, and the 25th and the 75 quartile present at the upper and the lower end of the box. And you see that we have black lines which and some lines beyond that. The region beyond this big black lines actually represents outliers or susceptible outliers, which have a value 3 times the interquartile range above or below our interquartile range. And the large black line actually represents the minimum and the maximum values obtained in our data set once these outliers have been removed. And this is how usually a box plot in real life will look like. It will not all values that you have in your data set will fall within your normal range, because some of them will be outliers as well. This is a very good description about the box plot. It's the link is there in the chapter. You can visit it and read more about it. Uh, the main advantage of using box plot is that it gives us a visual representation of the statistical values present within a data set. Also tells us how many values are outlier and how many values are within the range, and how much amount of cleaning needs to be done. This brings us to the end of the second chapter. Now let us move to the third chapter. And if there are any questions, I still don't see any questions, so okay, now I see one. How can you count the NaN values? How do you calculate mean over row rather than a column in a data frame? So in order to calculate mean over a row, you need to subset the row itself. And once you've obtained that subset of row, which is nothing but a list that will be returned, or a series data structure that will be returned, then you can perform the mean operation. So what we actually need to do in order to have a mean over a row is to subset that row and then call the mean operation. And how can we count the NaN values? One basic way of counting the NaN values will be that you obtain the length and you obtain the count, and you subtract the length from the count. As we saw in our uh, analysis, that the length of our data frame was 4. You see, the length of the data frame was 4, but the count value obtained was 3. Now, if I subtract my length from count, I get a fair idea about, okay, so there is at least one row which has a NaN value, or it might have a what you can say, it might have a value that cannot be computed. I hope that answers your question. Let us move to the third chapter, which is about subsetting the data frame. Now, when we talk about the mean, and I said that you need to subset the row, this is where you can see how to subset the row before you perform the mean on it. So this is the data that I'm generating, which is nothing but a list of lists where I have numbers from 1 to 5, and then I have another list which is nothing but a multiple of 2, 3, 4, and 35 present for this present in my data frame. And I am creating the data frame from that. I'm also giving the index value, that is the value for each of the 5 row, to be V, W, X, Y, Z, and the names of my column to be A, B, C, D, and E. So this is what my data frame looks like. I have my rows having an index associated with them, or a label associated with them, or the names of V, W, X, Y, Z, and columns with A, B, C, D. Now subsetting of my data frame can be done easily by using the column names. That is, I can only obtain a list having all the values present in column A, or I can use the label functions, which will use a combination of the labels A, B, C, D, E, and V, W, X, Y, Z, and subset using those. Or I can use the index, which is nothing but which will replace A as 0, B as 1, C as 2, and so on, and again V as 0, W as 1, and so on. Or I can use a combination of both of them. Let us see how can you obtain only a given column out of the data frame. So when I do my data frame in brackets, I specify the column name, then it will give me all the values associated in that column. So it will give you the values of each row, but for that column, as we can see here, only this first column A will be returned. I can also get the same value by doing data frame dot followed by the column name. This is what my original data frame is. We will again and again see the original data frame so that it acts as a refresher as to where the original data frame is and how we obtaining and how are we obtaining the subset. Now in this function, I want to obtain subset which has column A, E, and C present in it. But in my resulting data frame, I am reversing the order in which E and C are present. And in my resulting data frame, it does not matter whether E was after C in the original data set or not. The result that we will obtain will be based on how I am listing the columns in my query rather than in my original data frame. That is why you see that even though in my original data frame C comes before E, but in our resulting data frame we have E coming before C. And you see the values for all the rows W, X, Y, Z, and V present for the columns A, E, and C. And this is how you can obtain a subset of the data frame for all the rows in your data frame, but for a specific number of columns. You can also subset your data frame using the labels. Let me refresh that here A, B, C, D, E, and V, W, X, Y, Z are going to act as our labels. In order to perform selecting our data set using the labels, we use the LOC operation or the location operation. When I say my data frame dot lock followed by the row that I want to obtain the data for, then I see that I will get the data that says 35, 70, 105, 140, 175, which is nothing but the data for the zth row. That is it. Pandas will say, okay, Z refers to which row, and then it will give us the value associated by that row, because I have specified my fifth row to be labeled by the value Z. Similarly, I can obtain more than one rows. Here I have given the list to be W and Z. So from my original data set, the Wth row, which is actually the second row, and the zth row, which is actually the fifth row in my data frame, will be shown here, and all the column values are present because we have not filtered on the basis of column. Now let us see how I want to how I can filter on the basis of column. When I do this, then if I go back to my previous result where I said my location operation to perform subset only on W and Z, then this is the result I get. Now imagine that in this data set you are subsetting only the first two columns A and B. In that case, you will be shown 2, 4, 35, and 70 as the result, which is what we are getting. So it is nothing but you go to this row and this row, and once you've obtained the rows, you slice down only the columns that are labeled here. A and B are labeled to be a part of the subset. Therefore, when we subset, we get only column A and column B and row W and row Z. Now, if you remember using the concept of arrays or in Python or in C, then you know that when for an array you specify the row index or the column index, or in a matrix when you specify the row index and the column index, then you obtain the value present at that location. Similarly, you can use the log operation to obtain the value at a given row and index position. When I give a log with W and A in this format, then it will go to row W and column A, and the intersection of that will be returned as the result, which in our case is the value 2. Again, a refresher of what our original data set looked like. And now when I perform the log operation on, let's say I want to have third row onwards, all the rows present in my data and all the columns present in my data, then I do this where I specify where the colon stands for the start, where the left hand side of the colon will be the starting point, the right hand side will be the ending point. The comma tells me that the first half before the comma represents the subsetting for the row, and the second half after the comma will be the subsetting on the basis of column. Right now we are subsetting only on the basis of row, which says starting from X. If I am not giving any value, then it means that starting from X until the end, which will give me the X, Y, and Z rows of my data set with all the columns. Similarly, I can do the subsetting from column onwards. In this case, I am saying that all my rows should be present, but my columns should be between C and E. So it will take C, D, and E columns in the result, and it will return all the rows plus those columns. Now, one interesting thing to notice here and to remember while using the log operation is that the slicing that is done includes both the starting value as well as the ending value. In general, when you're performing the slice operation in Python, then it goes from start to stop -1. But in case of the LOC operation, it goes from start till the end and includes both of them. And this is how we end up with C, D, and E. Now, if I do the log operation giving my start and end to be empty for both row and column, then it will in effect return me the whole data set, which is as good as printing the data set itself. I hope that this subsetting or using the labeling is clear to you. In case you have any doubt, you can share your doubt in the chat, which has been which is this link. I don't see any questions here, so we can move on. One more thing that can be done using the lock operation is that instead of returning the original value, you can return a Boolean result based on the condition. For example, here I am saying that my subset will be all the rows but columns B to C, which is in effect column B and C. But when you obtain that data set, for each of the value, you perform the modulus operation and check whether the result is 0 or not. And if it is 0, then replace that value with true, and if it is not, then replace that value with the false. And you can, instead of using this operation, you can use any other operation which can yield you a Boolean result. Now you can then perform some operation on the true and false value to obtain more insights depending on why you intended to do that at first place. For example, by doing the mod equal to 2, I obtain whether the number present in this value position is an even number or not. And if I have, and then I can have a condition that if all the numbers present in my column is an even number, then perform some operation on it, and if it is not, then perform some other operation on that column. So this is how the Boolean operation and indexing can be helpful. We can also subset based on the index value. The index value is nothing but the index as we know, where instead of A, B, C, D, E, the index for my column A will be 0, the index for my column B will be 1, and so on. And the index instead of being V will be 0, 1, and so on. That is, I'm going to use the indexing method as we know for any given matrix in Python starting from 0 for both row and column. The another difference between the ilock and the lock operation is that, remember, in the lock operation I said that the slicing operation takes the start and the end into consideration. The ilock operation does not. It is as good as at slicing as the original slice function. Or another way to remember this is that the lock operation slicing is an exception to the general rule we know. Now, when I do the ilock operation giving the index as 2, then it will pick the second row, which is 0, 1, 2, which is the row label X. And it will return me the values for that. As you can see, the values for this matches the result that we have obtained. Similarly, when I do 2 colon and I can give a end index, and when I don't give an end index, it means from second row onwards I want all the data, then this is what is returned. This is our original data set. Now, a little tricky one. Let's say I want to obtain a subset of the data set that goes from the first row until the third row and the first column until the third column. Remember that the ilock slicing will ignore the last value and take last value minus 1. So what we get in effect is the first row and the second row, and then the first column B and the second column C. So here, before the comma, it represents the subset or the slicing you want to do on the row, and after the comma, you have the slicing that you want to perform on the columns. And if I do not give any value for my row, then it will give me all the rows, but only for the specified column B and C, which is the first and the second column, ignoring the third one. I can also give a list of indexes. Let's say I do not want a continuous a series of rows and columns, but I want first row and then the third row and then the seventh row, or I want the second column and the fourth column and then the 10th column. In that case, I can specify the list of rows and the list of columns on which the subset should be done. Now let's go back to our original data set where I am saying that I want row 1 and 3, which is row labeled W and row labeled Y. And once I have obtained these two rows, I'm saying I want the column I want the column indexed second and fourth, which is 0, 1, 2, the third column C, and the fourth column E. And this is the data set that we get once we have done the operation of obtaining only the rows and columns present within the list. Similarly, I can tell the iloc operation to return all the columns but only specific, all the rows but only specific columns which are present in my row, which is here in case second and fourth, which is C and E. But instead of subsetting on the rows, it will return me all the rows. Similar to the log function where you can obtain a one single value, iloc operation can also give you one single value. Again, you specify the row index and the column index. So here my row index is 0 and my column index is 0, and it will return me the value present at the 0th row and the 0th column, which in my data set is the 0th row and the 0th column value 1, which is what is returned. Some time ago, we had another function in Pandas which was used for subsetting, which was the ix function, which used a combination of labels and indexes, but it has been deprecated for the reason that it affects the performance. When I'm using the log function, then Pandas know that it has to treat the values that I'm telling it to subset on as labels. And when I'm using the index function, it again knows that I'm telling it to use the indexes. But when I give a combination of labels and indexes, some conflict might arise, and it has to perform calculations in order to determine, okay, these are the labels and these are the indexes that needs to be used. For this reason, this function of combining both of them was deprecated. But if you want to use or somehow have a need to use that, then you can always subset on one and then use the other function followed by it. For example, here I'm subsetting the data frame on my column A, and then I'm saying that in this column, I want the value present at the location index 0, which is in effect telling me that my 0th column and my 0th row value should be returned to me, which is 1, as we saw before. Now, this is how subsetting can be done in Python or in Pandas, and you can use the lock for the labels, iloc for indexing, or based on your need, you can have a combination of the two, and then you can perform operations on that subset of data. But remember that the results that are returned need to be first saved into some data frame before you can use those results. Otherwise, you will lose them. And this brings us to the end of the third chapter, which talked about subsetting a data set. In the next chapter, we will be talking about how we can merge two data sets. I don't seem to have any questions. If you people have any questions, then please add them to the chat link here. Okay, now when I talk about merging the data frame, let us understand the need for merging the data frame. Sometimes it can happen that you are working on, as I said, Pandas is very good at handling different file formats. Let's say that you are working on three separate file formats, and you have three data frame for each of those file formats, and you did some calculation, some cleaning on them, but now you feel that you need to aggregate all that information. This is where the merging of data frames come into picture. You can use the concat, the merge, and the append operation or append functions that will help you perform the merge operation. This is the sample data frame that I'm going to use as my first data frame, which looks like this. It has an index 0, 1 to 3, columns A, B, C, D with values 0 to 3 for each row. And then I have another data frame, B2, which looks something like this. So I have my first data frame B1, which has columns A to D but rows 0 to 3. And I have my second data frame, again having columns A to D but rows from 4 to 7. Let us see what happens when I concatenate the data frame. Now the command is pandas.concatenate function, and then you give the list of all the data frames that you want to concatenate. So you can have more than 2 as well. And when I combine, this is the result I get. It combined vertically, which means that the second data frame was pasted below the first data frame. And in this way, we see that the first 4 values from the index 0 to 3 belong to my first data frame df1, and the values from 4 to 7 belong to my second data frame df2, and both of them have been combined. And the combination, and remember when in the introduction I talked about labels and indexing helping us in auto formatting and compilation of the data frame, this is where it comes into picture. When my data frames were combined, then it picked the label A from the second data frame and the label A from the first data frame to be one and the same label, and it concatenated the values along the same column A. Similarly for the rest of the columns. In fact, while concatenating, I can even give another set of index in form of keys, which is nothing but introducing an hierarchical index within my result. Here, I set my key to be first and second, which means that my first data frame will have a key or an index named as first, and my second data frame will have a key or an index named as second. The use of this is that I can then obtain a subset of the data of my resultant data set based on the first and the second labels that I have obtained. For example, in my result, when I select only the data points which are added to the key second, then I in effect obtain my second data set, that was df2. Similarly, I can specify my location based on my key number first, and I will obtain the subset of the data that is associated with the key first, which is nothing but my first data frame. Again, let's see, this is the first data frame, and now I have another data frame which looks somewhat different from my original data frame df1. Here I have columns B, D, and F. Now B and D are column values that are present in df1 as well, but F is a new column that is getting introduced. At the same time, row index 2 and 3 are present in my previous data set as well, where I have 2 and 3 in my df1. But I see that index values 6 and 7 are getting introduced in my data frame. Let us see what happens when this is merged. Okay, I obtained a big data set consisting of some non-values. Let us see how the system arrived at this result. So from row 0 to 3 and column A to D is actually my original data frame 1 with all its values intact. Then when I said combine the third data frame introduced a new column and new rows with it. So a new column F was introduced, but it did not exist in my original data frame as you can see. Therefore, the values for the F column for each of the values present in my first data frame is none, which means the system cannot determine what value should be given to the column F and row 0, which belongs to my original data set, which did not have this column. Similarly, when now in the second half, you see that we have row index 2, 3, 6, and 7, which are nothing but the indexes present in my third data frame, as you can see here. And these values are associated with column B, column D, and column F for each of these last four values. But I see the NaN value present for column A and column C. That is because my third data frame does not have any row or any column labeled A and C. So when this was combined with a data frame which had existing columns as A and C, for those respective rows, I have a NaN values. Now, one thing you must have noticed is that we have index 2 and index 3 repeated. That is because for my first data frame, index 2 and 3 were present, and then again in my second data frame, index 2 and 3 were present. By default, the result will let the indexes be duplicated. If you want them not to be duplicated and if you want the duplicates to be absent, then you have to specify the duplicate index to be set to false, so that you can have only so that the duplication of indexing is changed. um, this is a little tricky, so let us revise this again. I have my original data frame that has columns A, B, C, D and rows from 0 to 3, and my new data frame has row 2, 3, 6, 7 and column B, D, F, where the column F and row 6, 7 are not present in my previous data set. And when I combine these two data sets, then for the column in my original data set which did not have the new column, the values will be NaN. Similarly, when I compare my second data set with my first one, which did not have the A and C columns, the values for those columns will be NaN. And this is how we combine two data frames when we place them one beneath the other. What if I want to combine my data set horizontally? In that case, I add an extra parameter to my concatenate function and tell the axis should be equal to 1. By default, axis is 0, which means that it will do a vertical concatenation. But when my axis is specified as 1, then it will do a horizontal concatenation. Now again, here from row A, B, from column A, B, C, D up till row 3, these first left corner specifies my data set df1, and then I have my second data set df3 with its column B, D, and F. Now again, remember that for my data set 1, there is no F column present. But since D and B column are new columns, because this is 0, this is 1, this is 2, this is 3, this is 4, I do not have this fourth column present in my original data set, so the value for it is NaN. Similarly, for my row 1, the value is NaN because for row 1, because my original data set has 0, 1, 2, 3, but my df3 data set does not have any row as 0 or 1. Therefore, the values will be none for the B, D, and F column. Previously, we saw that the value for the first data frame was none only in the DF column. That was because I was not adding any extra values in my row other than the F column. But here I'm adding two extra values in my row, which is B and D, for which the values don't exist in my first data frame. That is why the last three values are none for row 0 and 1. Interestingly, for row 2 and 3, you see them that they are completely filled. That is because index number 2 exists in my first data frame and index number 2 exists in my second data frame as well. Similarly, index number 3 exists in my second data frame and index number 3 exists in my first data frame as well. Therefore, the values for this row is present in both the data frame and all the values are present. Again, when I go back to my second data frame, which has rows 6 and 7, in this case we see that my original data frame does not have any row 6 and 7. Therefore, the values of row 6 and 7 for the first four columns is none. I hope I was able to explain this operation of concatenating two data set horizontally. A simple way to remember this is that when you are concatenating vertically, you're concatenating on the basis of the columns, and when you're concatenating horizontally, you're concatenating on the basis of row. Therefore, when you're concatenating horizontally, all the columns that are present, all the rows that are present in both the data frame will have complete values, and any of the row that is missing in either of the columns, for example, row 1 and 2 missing from my second data frame, or row 6 and 7 missing from my first data frame, will be filled with none. Similarly, if I go back, then in this case, the columns that are not present in my second data frame are filled with none because they are present in my first data frame and not in the second, and the column that is present in my second and not first is filled with none. Does anyone have any question on this? Let's move on. Now we saw that when I did the merge operation, I obtained NaN values. What if I want only those rows which do not have a NaN value? In that case, I specify another parameter, which is the join operation, and tell it to perform an inner join. This is similar to the concept of inner join in SQL, where while it is combining on the basis of row, because I've specified access to be 1, it will give me only those rows that are present in both my first data frame and in my second data frame. As we know that only row 2 and 3 are the row numbers that are present in both the data frames, therefore only those two rows are returned. Now if I go back, then my original data set D1 has row 2 and 3, and my second data set DF3 also has rows 2 and 3. And when I perform concatenation and specify the join type to be inner, then an intersection of the row values is taken based on the access specified equal to 1, and only those two rows are returned. Similarly, I can perform the join operation while I'm concatenating vertically as well. In this case, it will join only, the join operation will pick the intersection of the columns that are present in both the data frame and return the result. Here in this case, we see that column B and D are returned. If I go back, I know that my original data frame had A, B, C, D as columns, and my second data frame has B, D, F as columns. And B and D are the common value or the common columns present in both the data frame that is returned when I do the join inner based on the columnar concatenation of data. Similar to the join equal to inner, you can perform all SQL like join operations on inner, outer, left, right based on one or more keys. In fact, the Pandas documentation has a very good documentation here where it compares the SQL operation with its counterpart in Pandas, and you can read more here. And as I said in the beginning, the real power of performing the merge operation comes when I am combining data set from different file formats. Because once you have worked a little bit on different data set, you want to merge them so that the cleaning and the analysis can be done more effectively, and you will have the bigger picture in mind. This is it about the fourth chapter. Let us now move to the fifth chapter. Please feel free to post any questions you have regarding the merging operation or regarding the subsetting operation that we studied so far. The fifth chapter is about dealing with the split apply combine operation, which is in a way related to the splitting is the group or by function in our SQL terms. The apply function comes from the functional programming concept of applying an operation on a set of data, and the combine operation will basically, after the data has been split and some operation has been applied onto it, it will combine the result into a specific data structure. So the split operation basically divides the data into groups. The apply operation applies a function on each of the group separately and independently, which means that the result of operation on one group does not affect the result of operation on another group. And once I have obtained the result, I can then combine the result of split apply into one data frame. Now, when I talk about applying some operations, then I can perform the aggregation or the reduction operation, which will return an aggregated result for the whole group, which means one value that represents the whole group. Or I can perform the transformation operation, which will return the same number of rows or the same number of data points as present in my input data set, but the data values being transformed. And when I'm performing the filtration operation, then it will discard a group or a group of values based on the condition whether it evaluates to true or false. Now, in the previous section, we did the splitting of data set on the basis of rows and columns, which is in a way, as you can say, subsetting or splitting. But the split that we are going to consider here will be actually based on the values present at that row and column. Previously, when we were splitting, we did not take into consideration the values that were present. In this splitting, we are going to take into consideration the value that was present. That is similar to the group by operation in SQL. So I have my data frame here. You see that two of the columns have the string values and two of my columns have numerical values associated with them. And I tell Pandas that I want to group them on the basis of the unique values present in my column B. Now I know that A, B, and C are the three unique values present in my column. And my group by function will divide my data, will then subset my data set in such a manner that all the values with where the B value is A are together, all the data set where the B value is B are together, and all the values where C value where the B value is C are together. When I perform the group by function, it does not return any result. That is because the group by function performs a lazy operation. In that case, when I call the group by function, it will tell me that yes, the function has been invoked. This is the object that is returned, but nothing has been done on this object so far. Now, when I call the groups parameter on the group by function, then it will return me what are the different groups present in my data set. Here it tells me that on the basis of the unique value present in my column B, I have three groups, group A, group B, and group C. And then it also tells me what are the rows that are associated with that group. Now let us go back to our data set. Here we see that the 0th row, the second row, and the fifth row are should be grouped together as A, and this is what we obtain. Similarly, for B, I know that my group should be the first row and the sixth row, which is what we are getting. Similarly, for C, if you want to obtain data present within a subset, then you can use the get group function. So here, after I have grouped my data frame on the basis of my B column, I call the get group function and ask the grouped result to return me only that group which is the B group, which is this one. It should have index 1 and 6 present in it, which is present, and it is also telling me what are the rest of the values for the columns that were not grouped. That is, for A I have 1, second and first, for C D, but for B the value is B and B because that is the group that I obtained. This was up till now what we saw was only the splitting. Now once I have obtained this group, I can perform some calculation on top of that group. That is where the apply portion of the apply combine comes into picture. Now here I am performing an aggregation function of summing the results. Now you know that now we know that in general I have a column as well, but A is a string value, which means that when I am performing the sum operation, the non-numerical column A is ignored and the result has only the numerical columns C and D present in it. And the result is that for my group, for my group B value A, the sum is 10. That means that if I group all the values present in my group A, whose column is C, then it should be 10. Similarly, for my group B, the sum of the column C should be 9. Now we can go back to our previous result where we got the group B and see that for the C column, the sum is 2 plus 7, which is 9, and 9 is returned to us. And similarly, the sum for D column is returned. Similar to the sum operation, I can group my data set and perform the mean operation, which will return me the mean of that group based on the column values, but only for the numerical data. Now this is something related to the split, apply, combine that I want to discuss, and I picked this from the documentation because this is really interesting to understand and see how it is working. So basically I'm creating an array of values, and then I'm saying that this array should actually form multi-index named as first and second. That means the first list in my array will be my first index, and the second list in my array will become the second index. And then I'm creating a data frame having value of column A as a list and column B being returned as a range or a list from np dot range is similar to the range function returning the value from 0 to 7. And once I create the data frame, this is what it looks like. The first is my first index, the second is my second index, and this is actually creating a first and second together are actually creating a hierarchical indexing. And then I have my columns A, B, and C, all of them being numerical. Now, I can perform grouping on the basis of my first and second level indexes that I have obtained. As you can see, in this case, I call the group by function on my temporary data set, which is this, the ftemp, and then I am calling the grouper level, which will tell the group by function which level of index should be used for grouping. When I am giving the level equal to 0, then from my data set, it will pick the first index to be the first level index to be my group by parameter, and then I'm telling it to do a sum. And this is the result that I get, which means that my data frame was grouped based on the values present in my first index, which are 4 unique values of bar, bars, foo, and quarks. And I have the result of the sum that I obtained for column A, column B, and column C for each of these groups. The add prefix function total underscore is actually adding a prefix behind the column name just to give it a better annotation. Now let us see if this is actually happening or not. For the first index and bar, I have the total of A to be 2. And if I see the column of A in the bar section, then I see that the sum is 1 plus 1, which is 2. Now, while computing the sum, it did not split on the basis of the second column because the split was done on the basis of the first column. So all the values of the second column values were actually ignored while calculating the sum. Similarly for column B, similarly for column C, for various groups. Instead of giving level equal to 0, I can also give the label value for that level. In our case, the label value for the level 0 label is first and the level 1 label is second. And when I perform this operation, I get same result because instead of specifying the value of level group to be 0, I'm specifying the value of level group to be 1. This operation is helpful when you have to deal with hierarchical indexing or level of indexes. Then you can perform this grouping on more than one index as well. Going back to our original data set, let us perform some more grouping operations. Now this time I am grouping on the basis of my column A, which means that it should give me 2 unique values because my column A has only 2 unique values, first, second, and so on. Then I'm saying that the group data that is obtained, perform aggregation on that group data. And what are the aggregation operation? The mean and the median. Now the result that I get is that for my column A, it will give me the groups first and second, and for each group what is the mean and the median for each column. So for column C present in the first group, what is the mean and the median value? Similarly, for my column C present in the second group, what is the mean and the median value? Similarly, for column D, what are the mean and median values for each of the group? You can also perform different operation on each of the group by giving a dictionary where the key specifies the column on which you want the operation to be performed and the value represents the operation that you wish to perform. In this case, I want to compute the sum for column C and compute the standard deviation for column D for each of my groups. Again, for my group first, I have the sum of the column C, which is 16, and for the same group first, I calculate the standard deviation for the values on the column D. Now, let us perform a transformation function. Again, before transformation, I have grouped my data on the basis of A, which again will give me two groups based on the value first and second. But I'm saying that for the group perform the transformation function where each column is value obtained at each column is multiplied by 2. When I do this, I get my transformed data set as something like this. Now here you see that once the transformation has been applied, the value at my numerical column C and D increased by a multiple of 2 because that is the operation that I intended to perform on the column. But you see that here the non-numerical column B is also present. This is because when you have a string and you perform string into 2, then it will actually multiply the string or concatenate the string that many number of times. That is why, since this is a valid operation on string, that is why we have the B column present as well, and you see that its value is concatenated. If you see our original data frame, then it has the value of B as only single alphabets and value of C and D as 1 to 8 and 2 to 16. But when you perform the transformation, then my transformed data set has value of B as AA, which is concatenation of A 2 times, and the value at the column C is multiplied by 2, and so is the value at column D. I can perform the other transformation functions as well. It might happen that some transformation function might include only the numerical columns. In that case, my transformed result will not have my column B. Now, filtering function, head and tail function which we used previously are examples of our filtration operation. So when I give my data set and ask the head function to be operated on it, then it will return me the first 5 values by default. And if I give any other numerical values, then that number of rows will be returned. In this case, I'm asking to filter only the top 2 rows, and that is what I get back. I can also ask the system to filter out the bottom 2 rows, and it will filter that for me. Now, you see that when these operations are performed, whether it is grouping or whether the operation is a transformation or a filtration, the combined operation is implicitly happening behind the scene, where the combined result is returned in form of a data frame. This is it about the split, combine, apply, where we group the data set based on the certain values in my column. and then I apply some numerical or some transformation on it, whether it can be an aggregation or a transformation of concatenation or some other transformation. Or I can, once I've grouped the data, filter the data, which will ignore certain rows and columns in my resultant data. That is it about the fifth chapter. Now let us move to the final chapter of the session. Do we have any questions? None so far. Okay. You can post your questions in the chat here and we'll take them up as soon as I see them. Let us now go to the sixth chapter. Now, the sixth chapter is nothing but a revision or a recap of all the functions and the functionalities of Pandas that we have seen so far. But let us be quick in doing this. So I obtain my data set. I see that its length is approximately the same data set, 600,000 values, and the columns, which will give me the unique column. Now I want to see how my data looks like. Then I am going to perform the head operation, which, as we discussed before, performs the filtration, and I get the first 5 rows. Similarly, I can perform the tail operation, which will return me the last 6 rows of my data set. We have only 5 minutes left, but this session, the sixth chapter, might take at least 10 minutes. So in case you are time bound, you can drop out of the session, and the rest of you who wish to continue can stay. I will complete the chapter and then end the session. Now, one thing that you must have observed when I did the head operation is that the price has a NaN value, which is not desirable when you are performing operations or analysis. I wish to ignore all the NaN values. So for that, I call the drop NA function, which will drop the rows which have NaN values present in them. And how I wish to drop them is by specifying the parameter value to be any, which means that in my data set, if any of the value in my row is a NaN value, as in case of the first 5 values you will see, then drop that complete row, irrespective of whether other columns have a value or not. If even one of the column does not have a proper value, then drop that column. This is what I'm doing. You can also call the all function, which will only delete the row in case all the values in that row is NaN. In this case, if all the values in this row were NaN values, then only it will be dropped. If there are 1 or 2 or even 7 NaN values, then it will not drop. But what I'm doing is any operation, which means that even if one value is NaN, then drop that value. And then I obtain my another data frame. Now the drop NA value is actually a form of a filter operation. And we see that my new data frame has dropped 4,240 40 rows, in which some of them might be having 1 or 2, or some of them might be having all values as NaN. Now I call the describe function on my clean data frame. The describe function will basically give me the summary of the statistics for all the numerical columns present. So it will give me the mean, median, the interquartile values, the standard deviation for all the numerical values that are present in my data set, which is the caret, table, depth, price, XYZ columns. But I also have some non-numerical columns present in my data set, and these are categorical values. That means that the value present in my column of clarity can take one of the values which is unique to it. Let us see what are these unique values for the non-numerical columns. So I see that my non-numerical column clarity has these many unique values. My non-numerical value cut has these many unique values, and similarly for the rest of the non-numerical columns. Now, one thing to note here is that depending on your data set, the non-numerical values can be ordered or unordered. For example, here the non-numerical value cut is an ordered categorical value. It means that the category of the cut being idle will actually have better score as compared to the category which is good, as compared to the category which is very good. That means that there is a certain order or a certain weightage associated with the non-numerical values, but it might not be the case always. And before you determine or before you transform these categorical values into numerical values for any analysis, you should check the description of the data set to see whether the values are categorically ordered or unordered values. In our case, the description tells us that the categories are ordered in nature. Similarly, for certification, they are ordered, saying that a certification obtained by GIA is better than a certification that says other, or the color where a color value of I might be better than a color value of K. Let us see what are the various how do these various non-numerical values occupy my data. That is, how many values of these different numerical values are present. So when I group my data set by the categorical value color, then I will have my groups based on the unique color values. And then when I'm doing a caret count, then it will pick only the only the column caret from my data frame, and it will give me a count on that, which means that for color D, I have 73,000 values present in my column caret. And similarly for all of these values. If I remove the caret value and do the count, then it will give me, on the basis of color, the count obtained for each of the column other than color. So for group D, there are these many values for the caret column, these many count values present for the cut column, and so on. Now, let us visually see how the various color values map when I do the mapping on the basis of caret column only. Now here in this function, once I have obtained my result until df group by color caret count, I ask that information to be sent to my plotting function and tell that the plot has to be a bar plot. And when I do that, this is the plot that I obtain, where it automatically labels the bar on the basis of the unique color value and tells me how many how many values for each of these colors is present in my data set based on the count obtained on the caret column. Now, since we had performed the drop NA operation on using the any operation, which means that my data set does not have any nan value present anywhere, which means that irrespective of whether I perform the count operation on the caret column or the cut column, the result obtained for one group is going to be same, as you can see here. So uh, when I perform the plotting on the bar graph for only the caret value, this in turn represents the data that we will the plot that we will obtain when we do the categorization or the summation on the basis of cut or price or any other column value. Similarly, I can perform the count operation on the cut value and tell the system to generate its bar graph. Here we know that the cut can take only three values: ideal, good, and very good. And again, I perform the count only for my caret column, and then the result of this is then passed to the plot, where I tell the plot to be of kind bar graph and the color of the bar to be red. And this is what I obtain. One important function that we can perform on the data frame is the correlation function, which will perform the correlation operation between all the numerical values that are present in my data frame. Here, you see that the diagonal value is always 1 because the correlation of the value with itself will always be 1. Now, perform a Boolean operation on this correlation function, it will return me only those. It will return me true in case my correlation result was greater than 0.7. Ignoring the diagonal values, you see that the correlation between caret and price is true. The correlation between caret and XYZ is also true. Also, the correlation matrix is mirrored across the diagonal. So the correlation value between caret and table will be the same as the correlation value between the table and column. Now, let us say I want to subset my data and obtain only those columns which have good correlation with the caret, which is the price, X, Y, and Z column, and they are all numerical columns. Now remember that we had non-numerical columns as well, but the correlation function ignored them. And for my subsetting also, I'm ignoring those columns. Now I can perform the subset operation using the log function, where I am telling the system to give me all the rows, but only for the list of column. Or I can perform the subsetting by specifying the set of columns for the data frame, or I can perform the subsetting based on the ilog function, where instead of giving the labels, I am giving the value of the index that is present for this label. So caret is label 0, X is at index 9, and Y is at X is at index 8, Y at 9, and so on. And all of these three types of subsetting will give me the same result. Now, once I have obtained my subset, I am calling the plot function to perform the scatter plot operation on the data present in my subset, where my x-axis takes the value from the caret column and the y-axis takes the value from my price column. Now, because this is a huge data set of 600,000 values, the graph will take some time to get generated. Now, here we see that a lot of values are cluttered on top of each other. A lot of data points are close by, but you see a general trend of the price increasing as the caret value is increasing, which is somewhat logical as well, because a diamond of a larger caret value should be priced more. But we see that here we have some places where the data is empty. Let us explore that region more. So here, when I am specifying my scatter plot, along with my x axis and y axis, I tell the limit of x should be between 4 and 6. So you see that now only the values between 4 and 6 are present. And here the trend is not that visible because all of them seem to be at the same horizontal level. That means that even within the caret value 4 and 6, it is possible that data present at the caret value 4 can have different price. Let us see this closely to observe what is actually happening here. Now I have given my x limit to be between 5 and 5.2, which will give me a very enlarged view of the original price scatter plot, which is somewhere 5 between here and here. Like it's just one strip of my data set that I am visualizing, and here I see that I obtained completely vertical plots, which means that even at a value of, let's say, 5.05, I see that for the same value of caret, the price value is varying. Now, this is happening because we have not taken into consideration other factors, whether it is the XYZ measurement or even the non numerical values like the cut or the clarity, which might be affecting the price, which again seems logical. Now, this brings us to the end of the sixth chapter. What this exercise helped us understand was the various functions that I can perform on my data and the basic visualization that the Pandas data frame gives us out of the box. Using this basic functionality of the plotting, I can get a fair idea about what information I can obtain from my data set. So let's say tomorrow I want to create a regression function that determines the price based on the various features of the diamond, then I know where to start because I have visually seen the effect of some parameters on the price. That's it for this lesson, and this actually brings us to the end of this session as well. If you have any questions and feel and want to have them answered, feel free to hang around. You can also post the question on the video and I'll follow up on that. You can have the link of the sorry, you can have the link of my slides or the notebooks that I used, and you can work on them. You can obtain the data set, and in case you have any doubt, you can even create issues, and I'll be more than happy to help you out. Thank you for the session.